Hey Rutgers, this is Dr. Kristen McQuinn. I'm assistant professor here at Rutgers University, and I'm here to answer your questions about space. The first question is, how far have we explored the universe, and how big is the observable universe? Well, the observable universe is enormous. Compared to what our spatial scale is here on Earth, it's almost incomprehensible. Even though we've been studying the universe with big surveys with our telescopes for many years, the actual fraction of the universe that we've observed is quite small. And as you look to faraway objects like faraway distant galaxies, you're actually looking back in time. What we've studied mostly is light from the universe, some light from the electromagnetic spectrum. The things that give us light represent only about 5% of the content of the universe. Another roughly 25% of the universe is made up of what we call dark matter, and then about 70% of the universe is this mysterious force we call dark energy. And we have very little constraints on dark energy, but we have a lot of upcoming telescopes and surveys that are designed to study dark energy and understand its properties and whether or not it changes with time. The next question, what's the cosmic microwave background, and how big is it? Well, that kind of relates to the first story of how big the universe is. We think the universe started as a big bang and has expanded ever since. And after a few 100,000 years of expansion, the temperature of the universe cooled enough that the elementary particles were able to join together and form neutral atoms. And when that happened, the photons could essentially fly free. They were no longer bouncing off electrons and other particles. And we call this time the point of last scattering of these photons. But as they traveled across the universe, as the universe is expanding, those photons expanded, and the wavelengths of light stretched to become longer, and we receive them as microwaves. And so this makes up the cosmic microwave background. A really cool thing about the cosmic microwave background was that it was discovered in the 60s by two people, Wilson and Penzias, right here in New Jersey. And so it just reflects, the intellectual capital in the great state of New Jersey. The next question is about the shape of our universe, whether it's flat or spherical, whether it's opened or closed, and what that actually means. If the universe can expand indefinitely, then we would say it is an open universe and the energy wins. And part of that at work is this mysterious force called dark energy that we think is helping to power the expansion of the universe and actually accelerating it at present day. But if the universe doesn't always expand and it starts sort of slowing down, we call that a flat universe. And the debate on whether or not the universe is open or spherical or flat has to do with this balance between energy and gravity. Some of these upcoming surveys that will study dark energy in more detail will help constrain that further. A couple questions are about whether or not the universe infinitely expands and whether or how there can be just no end to the universe. And so this gets back to the question of whether or not the universe is open or closed or flat. So if it's continually expanding forever, this would be the open universe, which we don't really think we live in. And whether or not the universe has an end, this is a tricky thing to conceptualize. If you think about the surface of a balloon, you can't really tell whether there is an end or a beginning or a middle. So if you were, say, an ant crawling along the surface of a balloon, you wouldn't have an end to the surface and you wouldn't have a starting point or a middle point. And so that's the best way I can conceptualize and describe how the universe has no end. Okay, next question. How do institutions calculate the approximate size of the universe, the numbers of stars, and things like that? So the way we calculate this in science is based on getting some kind of representative sample or empirically constraining what we think the natural number of things are, and then studying the physics behind it so that we can scale those numbers up. And it really is an estimate, it's not an exact number. It is based on local measurements, understanding the physics, and then scaling it up to what we see in the greater universe. How do black holes work? And is it possible we're on the other side of a black hole right now? Okay, so a black hole is formed, we think, when you get a very dense concentration of matter in the universe where the gravity overcomes any force holding that object up. But if the energy source goes away, like at the end of a star's life, then gravity can win and pull in part of the center of the star into extremely dense matter, so much that gravity just overtakes any energy support it could possibly have, and it basically disappears into a finite point in space called a black hole. So it's a theoretical construct, but we have made observations around what we think are black holes, and they can come in many sizes. So there isn't really another side to a black hole. There's either just, you can have mass inside of a black hole that can never escape, or be outside of a black hole. Okay, next question. Do I believe that aliens or foreign life exists? I really do think that there is life out there in the universe outside of the Earth. Throughout our history as humans, anytime we've thought we've been in a special place in the universe, we've figured out that we're wrong. But the second reason I think that there's life out there is really based on a statistical argument, is that we are on one planet in a galaxy. The galaxy has billions and billions of planets, and there are billions and billions of galaxies. And to think that we have the only conditions where life can form in that large of a number is highly unlikely. The advanced state of that life would really be an open question. Next question. What is the most interesting planet or galaxy as a whole that I've come across? Well, that's easy. I have a favorite galaxy, and its name is Leo P. It's a galaxy that's relatively nearby our own Milky Way galaxy, but it is about 10,000 times as small. So it's this tiny little system that we discovered about a decade ago, and we've been studying it in many wavelengths of light since then. It's my favorite galaxy because it has some really interesting properties, and it pushes the boundary of what our understanding of galaxy and structure formation really is. I am leading a couple programs with the NASA's new James Webb Space Telescope, the JWST, and one of my programs is focused on this little tiny galaxy, Leo P. We've just gotten new observations this past April to study the galaxy and try to do what you might think of as an archaeological dig for some of the lowest mass, oldest stars in the galaxy. So definitely my favorite galaxy, little Leo P. The next question is, what's the closest galaxy to the Milky Way, and have we seen photos of it? So our Milky Way is, a big spiral galaxy. But around this big spiral galaxy are orbiting a ton of very small galaxies. The galaxies are pretty close to us. Many of them are so tiny they're no bigger than a star cluster and really faint and actually kind of hard to find. But there are two of these satellite galaxies that are actually a little bit bigger than your typical satellite. They're called the Large and Small Magellanic Cloud. And they are big enough and have enough star formation going on that we can actually see them with the naked eye. So if you're in the southern hemisphere and looking up in a dark sky, you can actually see both of these galaxies orbiting, even without a pair of binoculars. And so we are feeling the gravitational effects of those galaxies, and they are definitely feeling our gravitational effects as well. How is our galaxy formed, and how does the spiral shape influence Earth? So in the very early universe, we had these little overdensities of material, of matter. The gravity in these locations was stronger than the gravity in maybe the neighboring region that wasn't as dense. And so if the gravity is stronger, then it started pulling in material from the surrounding locations and getting bigger and bigger. And so you're adding dark matter and normal matter into these systems. They're gravitationally bound, and they form the first galaxies. Over time, these systems continue to grow, but they also merge with one another. And so the spiral shape doesn't heavily influence our everyday experience or life. But it does create some absolutely beautiful images of galaxies, and it also helps us understand how galaxies have evolved over time. I want to say thank you to everyone who sent in questions. This was super fun. For those in the Rutgers community, I look forward to seeing you on campus. And look out for the next video to answer your questions.